these videos already? Or you guys don't need? You never watch the videos, right? You do, Andrew? Is it useful?
Yeah.
Okay. So, as I said, we're going to do chapter 19. It's about impulse momentum. Let me share the screen. It's about impulse and momentum for rigid bodies. So again, I repeat that we went through the same steps for particles, kinematics, Newton's second law, work energy, and impulse momentum. We did the same for rigid bodies, kinematics, Newton's second law, work energy, and now impulse momentum. And we briefly discussed at the beginning of each chapter for the rigid body that what is the major difference between particle and rigid body. Can someone tell me what is the major difference between particle and rigid body, which creates new equations, new terms, and everything? Haojin, what is the major difference or addition for rigid bodies that we didn't have for particles? This should be easy to answer. What we didn't have in chapter 12 to 15, now we have in 16, 17, 18.
Rotation of the rigid body.
Rotation, right? You saw that rotation creates extra equation in kinematics, right? Angular velocity, angular acceleration, they all contribute to the motion of a particle or another part, a point on rigid body. All omega cross R, alpha cross R, those terms were generated by the rotation of the rigid body. In chapter 17, we saw that rotation creates torque and moments, or torque and moments create rotation, and that gives you extra equation. In chapter 18, we saw that rotation creates extra term for kinetic energy, right? Half I omega squared. And also the rotational force, if we call it that way, which is torque, moment, couple, right? They also create extra term for work. Now that we are in impulse momentum, I guess we should expect something similar, right? That we had linear momentum, we should expect to have something similar for angular motion, right? And that is what separates particles from rigid bodies. Does that make sense? So I try to give you the big picture of how rotation creates extra terms or extra equations that allows you to solve problems. Now, with that kind of brief introduction, we're going to talk about angular momentum of a particle. This is kind of new for particle because we did not have angular term for kinetic energy for particles, angular term for work for particles, but now you'll see the way we define angular momentum, you can define it for a particle. Then we talked about the momentum of a rigid body, which is going to be a kind of momentum version of the equations you had for kinetic energy and, you know, moment in previous chapters. Then after we create an understanding of how momentum of a rigid body is calculated or determined, then we're going to start principle of impulse and momentum. You expect something similar to work energy equation, right? The general concept was the same, just you had extra terms here. The general concept is the same. We're going to have like extra equations. And then we talk about conservation of momentum. Because we have angular momentum and linear momentum, we can talk about conservation of angular momentum and linear momentum. And then we have impact. Here we call it eccentric impact. You'll see why, because we have dimensions and you're going to have offsets between the impact point and the rest of the rigid body. So this is what we're going to talk about. Now, I know this list doesn't mean anything because we haven't discussed any of them. But after we go through the chapter, when you come back to these slides, you see each one of them one by one to review. I think you should have a good understanding of what's going on. So this is how we define the angular momentum of a particle. Technically, the angular momentum of a particle is the moment of linear momentum, right? Which means if you have a particle with velocity, its linear momentum is mv, right? And this mv is a vector. Similar to the way that we calculate the moment of a force. How we calculate the moment of a force? Let me switch to the tablet. So, oops. So I can explain this better. And you have reviewed and learned about this in statics, but I'm going to briefly review to see what we're talking about. So let's say this is like a plane. I try to make it like 3D. Then the vertical axis or z-axis is something like this, right? You can have like X and Y like that. And imagine you have a force F. Right? How much this force F create moment about this axis? If we want to calculate moment of force F. Do you guys remember how we do that? We were used to determine the, let's say, you know what, I'm going to make this kind of a little bigger, so, right? If this is the position vector of where F is applied, right? And this angle between them is theta. What we do is this. We determine the vertical distance, this d, and the moment of the force is going to be F times d, right? Now, if you look at this angle or this angle theta, this d is going to be r sine theta times F, right? And you remember when we have two vectors and sine theta between them, we can write it as r cross F. And this is going to be a vector m, but because it's in z direction, when you have planar motion, this is always m is going to be like some m times k always, right? And if you use the right hand rule, and let's say this is your right hand, right? This is your tongue. Sorry, my drawing is not as nice. Let me just try one more time. If this is your tongue, right? Then you get like this. This is the direction of rotation, right? And this is the direction of vector. And this is like right hand of Mickey Mouse or something, but this is still right hand. Okay. So because it's always in Z direction, we usually don't use it. Again, if you have a 3D vectors, force is this way, R is that way, like in robotics, then M is going to have any point. So this is a moment of a force, right? Now we're going to repeat something similar for linear momentum. Let's say, you know what? I'm going to use this all together to show how similar they are. And I just changed the names. Let's say we get rid of this. We'll get rid of that. I'm going to get rid of that. Okay. Right. Now, let's say we have a particle with velocity. So this is a particle with a mass of m and has velocity of v, right? So the linear momentum of mass m will be what? Is m times v, right? Does that make sense? This is what we did in chapter 15. Mass times velocity is a vector. We call it linear momentum. Now, here, look at here. To define moment of a force, I got force and that position vector cross, right? Now here, to find moment of linear momentum, I'm going to repeat this equation. Instead of F, I'm going to put linear momentum, right? So we call it H, and it's going to be R cross MV. So we call this angular momentum. Okay. So the angular momentum is defined as the moment of linear momentum and is obtained using this. Again, H is a vector. But if you are, again, in plane, R is inside the plane of motion, MV is inside the plane of motion. Their cross product using right-hand rule. Again, let's go to the Mickey Mouse. Oops. Right hand, right? And if this is the direction of angular momentum, the vector H is in this direction, which if you have in plane motion, H is always in Z direction. And you can simply write it H as a vector is H times K. Again, this is for 2D motion. If you have a general 3D motion like robotic stuff, then it's going to have IJK and it's going to be more complicated. Does that make sense? So that is how we define angular momentum. Oops. Angular momentum as moment of linear momentum. Force was moment of force cross product, and that's we don't call it moment of force, we just call it moment. Moment, torque, couple are same, right? But here, the linear momentum could result angular momentum if you have an axis and things are measured with respect to that axis. Any question about the basic concept? Looks good. Isaac, are we good?
Yes.
Okay. Now let's go back to the slides. And remember, because we always measure the moment about an axis, we put the subscript O here to show this is moment about axis Z that goes through O, right? Now, let's go back to the, this is just a definition of angular momentum of a particle. And I think I probably should go back to the slides and derive this step by step so you can follow. So let's go back to the tablet. And see how we do this. Now, I defined H about O here. Oh, I think we lost the sharing thing. Let me see. Let me do this one more time. So I got H about O defined as R cross mv, right? This is velocity of the particle. This is the mass, obviously, and this is position vector of the particle. Okay. Now, we're going to review Newton's second law. Just keep this here for some time, for this guy. Okay. If we go to the Newton's second law, you remember summation of forces for a particle, everything is about particle for now, was equal to ma, and you can write m v dot, right? Any question about this? You're good? Okay. Now, let's multiply or cross product this from the left by r. If I do that, I can write r cross summation of forces equals r cross mv dot. Can I do this? Yes or no? You know, mathematically, if you have an equation, the two sides of equation are the same. Whatever you do with this side, you can do with the same side. So I don't see problem with that. Okay. Now let's keep this here for now. I'm going to keep here for now. And try to find the time derivative of this. So H about O is R cross mv. The time derivative gives you d dt of h about O is equal to d dt of R cross MV, right? Again, you have an expression that the two sides are the same. You can take the time derivative of two sides. Any question about this? How I'm going to do this one? Chris, let me know how I can expand this.
I'm not sure.
You see, this is like the product of the two expressions. We have done this before. When you have cross product and you have ddt, you get the ddt of the first one. Let me just write it down. This is going to be dr dt cross mv plus r cross ddt of mv, right? It's like a regular product. How much is dr dt? The time derivative of position vector.
Velocity.
Velocity. So you're going to get v cross mv plus r cross m is constant, so you're going to get m v dot, right? For a particle, m is constant. Now someone tells me how much is this guy?
Isn't that 0?
Why?
Because V and V are in the same direction. There's no cross.
Yeah, cross of any vector with itself, because it's going to have sine of theta, and the sine of theta is 0. So technically, this is going to be 0. And if you get this all over here, you're going to get d dt of h about O, which was, remember, the angular momentum of the particle is equal to r cross m v dot, right? Now, have you seen this before? Go and check your notes, see if you have seen this before. Like 5, 6, 7 lines back. Kelly, what this represents?
That's like the moment of linear momentum.
No. Linear momentum is mv. There's no dot. With the
Is it
dot.
of summation of force?
Exactly. You see, it was here, right? So I can replace this guy with that guy here. And if I do that, I'm going to get, okay, d dt of h about O is r cross summation of forces. I can write this as h o dot, right? Just to make it simple. What is this guy? And if you go few lines back more, I'm going to show you. So R cross F is technically moment, right? Is it? So here, this is technically summation of moments. What? Oh. So this is the final equation for particle. So the change of Angular momentum. Of course, it's the rate of the change, right? Because it's dot here is equal to sum of moments applied, right? It's almost like summation of F equals mv dot. Here you have summation of moments is ho dot. This is for linear motion. This is for angular motion. And you may say, we didn't have angular motion for particles because particles doesn't have angular motion, but with the way we defined angular momentum, it kind of makes sense, right? Now, this was a little messed up. I'm going to go back to the slide and show you the clean version of it. If you printed the slides, you can just write it down. So, oops, we came up to here. R cross F is R cross mv dot. And then ho dot ddt of this, we get this one, that one. V cross V, as we said, is going to be 0. Then it's going to be R cross mv dot. And then using this, summation of moments are change of angular momentum for the particle. That was the whole process. And I'm going to pause here for 30 seconds if you want to write this down. I don't know how many of you print the notes. If you want to write it down in the notes, because this kind of looks more brief and nicer. Now that I explained it with all the schematics, this may be easier to follow. Any question about the whole process? Looks good? Okay. So now that we defined the angular momentum of a particle, we can define the momentum of a rigid body. We're going to use the same process. For the linear momentum, again, you have this potato-shaped rigid body. You put your reference points on one point on the rigid body like P. Each particle or each small, infinite or infinitesimal part of the particle could have velocity of VI. P has VP. You're going to have a center of gravity, which has VG, right? Its own velocity. So for the linear momentum, you're going to add all the linear momentum of these tiny particles, which is summation of MI VI. And that is the definition of center of gravity is going to be MVG. So for linear momentum, you can use center of gravity, its velocity times mass is going to be the linear momentum, right? That is technically the definition of center of mass. For angular momentum, you're going to have to add angular momentum of any of this, for example, MI, VI, and cross with this R and add it together. So all the angular momentum about point P, remember angular momentum has to be about a point because it defines rotation. Angular momentum about point P is going to be the summation of angular momentum of each tiny particle, right? For I, like mi, vi, and then cross ri. And if you write ri in terms of x and y, expand it and write the velocity of vi in terms of velocity of p and cross product and all of that, and expand it, and the derivation is in the textbook, we're going to end up this. H about P is VPX my bar, VPY m bar x, mx bar, and plus I about P omega. If you write all the relative velocities with respect to center of mass, remember, this is still H about P, but you can use the velocity of center of mass, VG, VG, IG, X bar and Y bar are again the distance between center of mass and X and Y axis. We had this in chapter 17 and 18, right? It's kind of quite similar to those expressions we had for kinetic energy and moment and alpha and all of that. Any question? You remember where we went after this? I said this is too complicated to memorize, and we want to simplify this. If we simplify this for special cases, for example, we always use two special cases. First, if I put point P on G, what happens? And also if point P is a fixed point, what happens? So if I put point P on G, let's go back here. If P and G are the same, this becomes H about G. Everything else is G. Y bar and X bar will be 0, right? Because X bar and Y bar are the distance of P from G. And if there's no distance, then they're going to be 0. Do you guys follow? Do you want me to draw G here and show it to you? Or we're good? Kelly, are we good?
I think so, yeah.
Everyone else? Izzy?
Yeah.
Jake? Good? Okay. Then the other special case is if you have angular momentum about fixed point. Again, if you go back here, if P is a fixed point, we usually use O for fixed point, H about O. Because it's fixed point, VPX and VPY will be 0. And you get just IO omega. So angular momentum about G, you get this. Angular momentum about fixed thing, you get that. And in summary, if you have translation, because omega is 0, H about G will be 0, you have only linear momentum. If you have rotation, H about O, IO omega. And if you have general motion, you're going to have linear momentum and angular momentum, right? So this is how we deal with the momentum of a rigid body. Again, we have linear momentum because of translational motion, and we have angular momentum too, right? Because of rotational motion. The change of angular momentum is caused by torque and moment. The change of linear momentum is caused by force, right? Any question? You guys need more time to write this, or you're done? Good. Okay. Now, let's talk about the principle of impulse and momentum for a rigid body. I'm going to go back to the slide, to the tablet, to write this down one by one and kind of derive it. It's not a big derivation, but just to show you where this thing come from. So we had summation of forces equals m v dot, and summation of moments was h about o dot. You see that this is like m dv dt, and because m is constant, we could get it inside, get it d dt of mv, and here you get d dt of h, right? Now, if I multiply this by dt, you're going to get summation of forces dt equals dmv, and here you're going to get summation of moments about o dt. It's going to be dh about o, right? If we integrate these two, over time, we're going to get from T1 to T2 summation of forces dt, and here simply mv2 minus mv1. And the second equation, this is equation 1, and now equation 2, we're going to get integration from T1 to T2, any time interval, summation of moments about O dt equals HO2 minus HO1. Moment about O, initial and final. And because we are in planar motion, we know that in two-dimensional motion, in XY plane, MO is going to be MOK, and H about O is going to be H about O. K, so it's always in K direction. I can drop the vectors and simply write equation 2 as summation of moment about O dt is HO2 minus HO1. Right? These two equations are the same because, again, in this textbook, in this course, we just go two-dimensional. We drop the vector because it's always in K. Remember, we use right-hand rule, and it's always in the direction of thumb, right? So that is what we have. You guys need time to write this down? And that is technically what we have in the slides. This is linear impulse. And of course, I use the velocity of g because VG represents, MVG represents the linear momentum of the system. And for the angular, you can write about O, you can write about G, depends on the case, right? That's how you get these equations. Any question? Are we good? Let me ask you this. If one of your classmates wants you to explain this concept to him or her, can you do that? For example, if I ask Kelly to teach this part of the course to the rest of the class, can you do it?
Possibly, yeah. If I
If you
think through it.
If you have the notes, if I give you the notes, say, Kelly, I'm sick today, go and teach this. Can you teach to the class?
Probably, yeah.
Izzy, how about you?
It may be a little hard.
The reason I'm asking this because, and sometimes you may study together, which is fine. And I have done that myself when I was, undergrad. The best way to understand if you grasp the concept is to try to explain it to someone else. Then they may ask a question, for example, why we don't have the vector sign for example, here, why we don't have vector sign here, but we have vector sign here. If you remember, okay, we are in an XY plane, so all moments and omegas and everything are in Z direction. So technically, this is always a Z component. You can explain it to that person. If you say, hey, that's a good question, I don't know, that means you need more practice. So the best way to figure out how deep you have understood is try to repeat the concepts in your mind or even loudly. It's like you are teaching someone. Or if you have a friend to sit together and do it, try to explain to one another. And same thing for problem solving. I'm not recommending that you copy homework problems from one another or quiz or anything, right? But when you are reviewing the concept and look at the problem, is that you're explaining, okay, I think this is how we should do this A, B, C, D, this is the process. And if you can do that, it means you have enough knowledge to do it, right? That's the best way. That's technically was the way I was used to study, with my friends and see who can explain. And sometimes one of us would explain better, sometimes not as much. That was the metric to see how well we have understood. And we try to answer each other's question. I mean, there's not one way to learn, but this is one way to review and see how much you've learned. So once in a while, ask yourself, can I teach this? Try to review the concepts and explain in your head and see how far it goes. Now, we defined the principle of impulse and momentum, right? The question is, and this is what we did for particles, what if there's no external impulse, linear impulse or angular impulse? If there's no impulse, initial momentum and final momentum will be the same, right? If there's no angular impulse, initial angular momentum and final angular momentum will be the same, right? And that is what we called conservation of momentum. For the linear, you use mvg1 equals mvg2. For the angular, you either go rotation about fixed point or general motion rotation about center of mass, whichever is easier, and you go from there, right? So I'm going to show you a video to see how this is interesting. If you have a rigid body and goes through some, interactions, but the overall forces are zero, the whole system is going to have the same velocity, right? For the angular momentum, it's slightly different. Before I show this video, I want to ask you guys, there are two fields of sports. One is like diving, and the other one is figure skating, right? You guys, I'm positive you have seen those sports, right? When the guy jumps over the dive board, there's no external force or moment or anything. The only force applying to his or her body is gravity that goes through the G, so it doesn't create any moment. But they can spin slower or faster while they're still in the air. Same thing goes with the figure skaters. You see, they can change their body position. There's no momentum. There's no moment applied to their body. But you see here, IG, if you change the IG, omega has to change accordingly, so the entire thing is same. And I hope this video shows well, because sometimes they don't. So I'm not sure how good you can see this. Of course, you can check the video later. When I started teaching this course many years back, I think this was the world record. And you're going to see how this works. This lady starts rotating around its vertical axis when her hands and legs are open. When the hands and legs are open, the moment of inertia about that axis is larger because you have more mass far from the body. When she starts taking the hands and legs close to her body, moment of inertia drops. But because there's no external moment, the overall angular momentum should be the same. When I goes down, omega has to go up to compensate for that. And this is what you can see here. You see, legs and hands are up. And now start collecting. And it starts turning very fast. It reaches 308 RPM. By that time, it was record. If you watch these sports in every performance, you see multiple occasions like this, that they rotate very fast, right? And that's how, let me see. So is the concept of angular momentum conservation clear now? Remember, if you have a rigid body, its mass is going to be the same. It's rigid, doesn't lose mass, doesn't gain mass, right? So before and after any interaction, if there's no overall moment applied or force applied or impulse applied, the magnitude of velocity will be the same. But for angular motion, is different. For angular motion, you can change I by, moving the parts of the rigid body on and off, or the system. So if I becomes bigger, omega becomes smaller. Or if I becomes smaller, the second omega has to become bigger. So the overall things is going to be the same. Make sense? Now, before we go, and I'm going to show this video, hopefully you can see this. This is another example. This guy is sitting on a frictionless or friction-free platform. This can easily rotate. We're going to give some angular momentum in this direction, and there's no external force. See what happens. We're going to give some angular momentum. You see, the angular momentum was in, let's say, X direction. The guy turned it and creates an angular momentum in Z direction. Because there's no external force, the overall angular momentum in Z should be 0. Now, the tire rotates let's say clockwise, the man with his own momentum has to rotate counterclockwise to balance this. And that's what happens. You see, it goes backward. It keeps it vertical. Again, everything zero. It keeps it backward and then rotates backward. This is technically conservation of angular momentum in z direction, because at the beginning there was nothing. Now, when you move forward or you rotate clockwise, the platform and the guy rotates counterclockwise to balance that. Do you know what is equivalent of that in the linear momentum? You remember the guy walks on the boat? Remember that? Let's say this is a boat and this is the guy. If they stay here, the overall linear momentum is zero. If the guy starts walking this way, it creates a momentum in this way. To make everything zero, the boat has to go opposite direction to balance that, right? This is exact same thing for the angular part. So the momentum the guy has, the whole system is in x direction. When you turn it to z, something has to balance that z to make it zero. Why? Because there was no moment or impulse applied in z direction. Everything should be zero. Does that make sense? So these are examples of, showing conservation of momentum. Now let's do some actual example. I'm going to give you 5 minutes of break before we start this problem, okay? It is almost 10:55. We're going to come back at 11, okay? And then we start solving problems. Just give you a few minutes to refresh. Okay, guys, let's get back and continue. Let me share the screen and see what we have here. So this is a simple example just to implement the concept of linear momentum, angular momentum, and things like that. You have a 30 kilogram gear that is fixed here, so it rotates about fixed point. To find its moment of inertia, it gives you the radius of gyration. You have a force 200 Newton here, and you have 20 kilogram gear rack, 30 kilogram gear, so the masses are given, the dimensions are given, the force is given. The problem says the time required for the gear to reach the velocity of 20 radian per second if it starts from rest. Let me draw this in the tablet. So for the gear, we show it with G. For the rack, we show it with P. The contact point is A, and I'm going to tell you why that matters. So M of gear is 30 kilogram. M of rack is 20 kilogram. The radius of gear R is 0.15 meter. The radius of gyration, kg, is 0.125 meter. The force applied is 200 Newton. And we want to find, so omega 0 is 0, or omega 1. Let's call it 1 and 2. It might be easier. Omega 1 is 0. We want to find how long it takes for omega-2 to be 20 radian per second, and we need delta T. Let's go to the tablet. And just a suggestion in general, when you solve engineering problems, I see most of you guys in your homework, you just start solving. It's always beneficial to summarize what you know and what you don't know, what is input and what is output. So that kind of gives you the understanding of how you solve the problem, right? Obviously, we have a time interval, we have a constant force. One way was to solve it using Newton's second law, find the linear angular acceleration, and find how much time you need to do that. The other way is to use impulse momentum. Okay. If I want to use impulse momentum, how I'm going to do it? You have an object rotating about a point, then you have an object translating, and you want to see how we're going to do this. So because we need to find forces and moments, obviously, I need to do free body diagram, right? So if that's the case, I'm going to do the gear here. So this is free body diagram, right? For the gear, you're going to get this guy. Look at here for a second, please. When I have a gear, and if I make this part a little larger, you're going to have something like this, right? And for the gear part, you're going to have something like this, right? So there's going to be contact here, but technically, it should be the other way. Right? There's going to be a contact here. When the rack goes this way, it's going to create a force of T here, right? Between the two teeth that are engaged. Can you visualize that? So if that's the case, at point A, I'm going to have a horizontal force T. Remember, this is not necessarily equal to P because a part of force P will be used to accelerate or to move the rack. And this is all ugly. Let me fix that. Of course, we're going to have reaction forces here. We're going to have mg and another reaction force going up. So you have like Ry and Rx, mg, and T. Do you have any other force? Now I'm going to ask you a question. If this was not a gear, it was like a disc and a plate with friction, no sliding, or with sliding, what would cause this guy to rotate? This force T, if you had a disc, you would have had friction force here, okay? So either the contact force of the teeth or the friction force, this is what is going to cause rotation. Does that make sense? Okay. Do we have any other force? And remember, if the force T, oops, if the force T is in this direction, it's going to rotate the disc like that, or the gear like that. Now I'm going to go to the rack. If this is rack, you're going to have the external force P here and the reaction of this force. Right? Any question about the free body diagram? Now let's write the equations of motion in terms of impulse and momentum. For gear, we have just angular motion about a fixed point. Let's call it fixed point O, right? If that's the case, I'm going to say H about O initially plus summation of moments about O integration dt is H about O finally. This is the principle of impulse, angular impulse and momentum. Right? Initial angular momentum is 0 because problem says it starts from rest. Moments creating about point O. Look at here for a second. This is point O. This is the force that creates moment. The moment of that force is going to be technically T times R dt from 0 to T. And here, H about O is going to be I about O omega 2. Again, I'm not using the vector sign because everything here is in Z direction. Because T and R are constant, technically, you're going to get T times R times delta T is I about O omega 2. And I'm going to write I about O, substitute it here to make it one step, less writing. How much is moment of inertia about O for the ring, for the gear? I'm going to ask Heisey, how I find moment of inertia about this point O?
I remember it's mass times R squared.
Mass times R squared. So you say I about O is M R squared. Is he right? I'm going to ask Yang if he is right.
I think it's right.
You think he's right? I'm going to ask Callie, and if she says he's right, we're going to accept it as a fact. Callie, is this right?
Is this for the sphere, the gear?
This is for ring, actually,
The ring?
like a hollow ring, very thin ring. This is a
And-
gear.
Yeah, I think he's right.
You think he's right. So you think a gear is like a hollow ring? Come on, guys.
But
Wouldn't it be like a disc?
It is not disc. It is like a disc, but it is not disc. Remember, if I do like, if you look at the gear, it's like something like this, right? If you look at the cross section, something like this comes, sometimes is filled, sometimes it's just partially filled. Then you have the middle part, which is the bearing, right? And goes here. This is the other part. And on top of this, you have this teeth. So definitely this is not a disc, it's not a gear, it's not a ring. It's a complicated shape, right? And that is why the radius of gyration is given. Please pay attention. Anytime radius of gyration is given, then I will be what? I is going to be mkg square times omega. Okay? Kg represents technically the moment of inertia. This is another way to give you moment of inertia. Instead of telling you moment of inertia is this much, they give radius of gyration, you substitute here. So this is the equation you get for gear. And if you look at here, we have two unknowns. One is T, force T, and one is omega 2, right? Therefore, we need to also consider the rack. Rack has translational motion. Right? And you know what? I'm just going to bring it here. If that's the case, I'm going to use principle of linear impulse and momentum. Which means M rack V1 plus integration of summation of forces dt equals M rack V2. If you notice, I did not use vector here because everything is in x direction. So technically this is like in x direction. Right? You don't have to put vector. Again, the problem says start from rest. This is 0 summation of forces in this direction. You're going to get P minus T delta T, this integral simplified like that equals M rack V2. Now the question is, how much is V2? Can I relate the velocity of rack to the velocity of gear? Kelly, how we can relate velocity of rack to the velocity of gear?
Can you, like with rotational motion, the velocity equals omega times r, and so you could,
Exactly. If you look at this point, point A, I can write it here, right? For point A, VA from gear is R omega, right? And from rack is just V rack, right? Remember, look at here for a second, please, everybody. If you have gear system, I don't know if you can see my finger, at the contact points, the 2 points have the same velocity, right? There's no sliding. The 2 points have the same velocity at the contact. And therefore, because rack moves forward and A belongs to both of them, technically, you can write V rack is R omega. And if that's the case, I'm going to simplify this and write P minus T delta T equals M R omega 2. Now you have two equations to unknown. This is 1. This is 2. You can solve for T and omega. Like, for example, from 1, you can calculate T, which is going to be M kg squared divided by R delta T times omega 2 from here. And then substitute to 2 as P delta T. I'm going to expand this minus M kg squared R delta T times delta T omega 2 equals M R omega 2. And because you know omega 2, you can calculate delta T here as, let me just give you the final number because this is too easy. Going to be 0.6125 second. Any question about this? So that was a simple example just showing you how you can use principle of angular impulse momentum or principle of linear impulse momentum. In this case, we use both of them because one object has rotational motion, one object has translational motion. The two objects are linked to move together because of the gear system. So you can create equations and solve them. Any question? Are you guys done writing this? Okay. Now let's go back to the slides. I'm going to solve this example. Here, you see we have a spool here, 30 kilogram, 2 blocks, block A and B are kind of, attached is not the right word, connected to this through the ropes. A rotates on a larger radius, B rotates on a smaller radius. The mass of each of them is given, block A 25 kilogram, block B 10 kilogram, right? And again, for the spool, the radius of gyration is given. Again, this is not a regular disc or ring or any standard shape. Because of the complex geometry, it gives you the radius of gyration. And it says, again, they are released from rest, determine the time required for block A to reach the speed of 2 meters per second. Okay. So let's just draw the thing here. I'm going to call the two radii RB and RA because one kind of relates to A, the other relates to B. And we go from there. So let's go to the tablet. Now, again, I'm just going to summarize the information given. So the spool has mass of 30 kilogram. I'm just going to call it MS for spool. MS is 30 kilogram. MA is 25. MB is 10. RA 0.3 meter. RB 0.18 meter. Radius of gyration is 0.25 meter, right? V1 is 0 for A, for VA1. VA2 is 2 meters per second. Again, we are looking for the time required to get this done. This is almost identical to the previous problem, right? In the previous problem, we had two objects, gear and the rack. Here we have three objects, spool, then block A and block B. So this is like block A. Oops. This is block B, right? And let's go for the spool like that. Okay. We can do this. We can go exact same steps. Get the free body diagram for the spool. Get the free body diagram for object A and object B, right? Or I'm going to do something different. So you can write it or you can pause. I'm going to consider the whole system as my system. Can I do that? Remember, we defined angular momentum for a particle, right? We defined this. So I can use this and get angular momentum of A and angular momentum of B, make them the whole system as one. Does that make sense? Now, if that's the case, do you guys follow? I want to show you these two methods are the same. And I want to show you how you can use the angular momentum concept to simplify solving a problem. Otherwise, what is the point of all this, right? So if I consider the whole system as my, well, system and get the free body diagram, this is going to be the system. Right? If I do the free body diagram here, I'm going to have the external force is going to be M AG M BG, right? And I'm going to have reaction forces like RY and Rx. You may realize that Rx is 0 because there's no other horizontal force, right? And let's call this center point as O. So this is point O. Does that make sense? Now that, you know what, let's just make O just, okay, this is point O. Can you see this tiny O? Now I'm going to use the principle of angular impulse and momentum for whole system. Okay, from the entire system. This is my system. The whole thing here, this is my system. Okay. If that's the case, we're going to have, because we have more than one particle, we're going to have summation of H about O at 1 plus integration of summation of moments about O dt from 0 to t is equal to summation of H about O Any question about this equation? Looks good, right? Let me clean this thing a little bit so, oops. Now that we know what the system is, I can get rid of this. Okay. Now, the system starts from rest, so no zero, no velocity, no angular velocity, nothing. So H about O will be 0. What creates moment about O here? You're going to have, look at here for a second, please do not write. Force mg, oops. Force mg has this radius and creates rotation this way. Force mg for B has this radius and creates rotation or moment in this direction. You may not know when we release this if B goes down or A goes down, but if you look at the numbers, MA is 25, MB is 10, it has a larger radius, so we're expecting that goes this way. So I'm going to consider this as positive. Okay? Then, summation of moments about O is going to be MAG, which is the force times RA minus MBG times RB. These are all moments. And because they're constant, this integral simply becomes delta T, right? Anyone doesn't follow or doesn't get this? Looks good? If you have any question, you can ask now. Don't feel shy. I can explain it. Because you get something like this, you have to be able to perform and do it properly. Okay, good. Let me get rid of these things to keep it clean. Now, summation of angular momentum. If I assume that this is going to go this way, my omega 2 is going to be this way, right? Let's clean these things also. So I have three objects that create angular momentum. One is the spool. The angular, look at my hand. If I keep my hand on the plane of tablet, which you can do if you draw the same way, I use my right hand and the angular momentum of omega is in top going up. Let's say this is positive, right? So you're going to get I about O omega 2. And this is for spool, right? Now, particle A also has angular momentum. How? This is the radius. This is the velocity. And if you look at here again, this velocity times this radius creates a moment or angular momentum same way, which is going to be positive, right? So you're going to get velocity times radius. It's going to be MA VA times RA. This is for block A. Do you guys follow? This is technically, look at here for a second. Forget about the spool. You remember we had X and Y? And it says if a particle has velocity of V, right? The moment H about O is going to be R cross MV, right? And R cross MV, this cross means you're going to use this distance D. So it's going to be MVD in terms of the number. And that is what we have here, right? Now, how about particle B? Is it positive or negative? I'm going to redraw the spool to see how it goes, because I want to get it a little bigger. If this is your spool, if this rotates this way, does this go down or up? B goes down or B goes up?
Goes up.
Goes up. So technically, if you want to get that cross product R cross MV for B, this is your velocity, this is your radius. What kind of rotation this creates? Same way, right? So technically B goes up, but because it's in the opposite direction, creates the same angular momentum. The sign is the same. Can you guys see that? If this is the radius and this is the velocity, tries to get it that way, right? Which is the same as omega 2 and same as MA VARA, right? So this is the same. So if that's the case, for block B, we're going to get it positive plus MB VB RB. They're all positive. So this is for block B. So technically, this principle of angular impulse and momentum gave you one equation. Why one? Because everything is in z direction. Now, if I rewrite this and kind of make it simple, you're going to get MAGRA minus MBGRB times delta T equals IO. And for IO, I can write again mass of a spool times radius of gyration. So we're going to get M spool kg square times omega 2 plus MA VA RA plus MB VB RB. The problem tells you how much VA is, right? VA is given. Do I know omega and VB? Because I don't know DT, that is the unknown we are looking for. Do I know VB and omega 2? Because if we don't know, which seems we don't, we need to find an equation for it. One of the Jakes, tell me how I can relate omega 2, VB, and VA so we get an equation out of it. Jake B, you want to say something?
I'm not really sure how to do that.
This is a part of chapter 16 thing. Look at this spool here. If this is the spool, and this is the rope going down with velocity of VA, can I relate omega 2 to VA? Because the rope is not going to stretch or shrink, right?
Right.
So if I do that, technically VA is RA omega 2.
Oh, shoot.
And same thing, if B goes up, VB is RB omega 2. So from here, you can find omega 2 is VA over RA, and then substitute here. So I'm going to give you guys a minute to do all of that, calculate your delta T. And I want everyone to please try this, because you're going to have to practice this. These are very simple equations. We have done it a few times, but if you don't do it yourself, it doesn't, click in your head. And tell me what you got. So I even don't have the solution for this. So I'm going to wait for you guys to finish. And see what you got. Do you guys get this number?
That's what I got.
Yep.
Okay, so that is how you do it. Now, you could use, as I said, separate. I know we are over time by a couple of minutes, but just bear with me for a second. We could do separate free body diagrams, like for A, you're going to get mg and ta. For B, you're going to get mg and tb. And for the spool, you're going to get ta and tb, right? And write linear momentum, impulse momentum for these guys, and angular impulse momentum for this guy. And then when you substitute t from here into here, you practically end up same equation. So you see, getting the principle of angular linear momentum. And I recommend you guys, if you want to see how it works, it will help you to understand. You can try this. You know what? Let's do this. I'm going to give this you as bonus problem. When you solve them separately. So you pick 3 different free body diagrams. Okay. Solve them, you should get the same number, obviously. Remember, the relation between velocity of A and B and the spool is the same, our omega thing. And TA and TB are not the same, obviously, because this is one object. I'm sorry, I missed it too much, but these are not the same forces, right? So you do this. You solve it as a bonus problem, submit it. I expect to get the same number, obviously, right? And then you find out if you replace TA and TB for this guy, you should end up same equation. So I recommend you to do parametrically and substitute to see if you end up this equation. So it kind of gives you a better understanding how these things work with the positive, negatives, and everything. Any question? And remember here for A, if A goes down, for forces, you're going to get mg minus TA, right? Because this is V, this is TA, this is mg, right? This should be MVA. For B, because B goes up, you're going to get TB minus mg times delta T is going to be MVB, right? Because this overcomes this to go up. And if you do that, you should get the same thing. Any question? Did you guys enjoy the class? It was good. Let me get the screenshot of the class. Yeah, I'm going to save the recorded video, obviously, post it later as is processed by Zoom and by the Blackboard. I'm going to create a link for the bonus problem. It's going to be due tonight, so I recommend you just to do it if you're not too hungry and you can take another 10 minutes. Do it right now. Everything is fresh and finish it and submit it, okay? We're going to continue with chapter 19 on Monday. I'm expecting to finish it on Monday. If we finish that, of course, we have a quiz on chapter 18. If we finish it on Monday, we can use Wednesday to solve some review problems from the entire book. And the next Friday is going to be your final exam. I don't know if you guys check the emails, but I think the course review, the evaluation link should be available. Have you guys seen it in your Blackboard? Is it available to do the course evaluation? It's going to take 5 minutes, probably less than that. Please take that 5 minutes, because specifically for summer course, you know, being around the noon time, you know, the 2-hour class and everything, I want to see how we can improve this, okay? So complete the evaluation, give me your comments. This is not like corporate, you know, evaluation things you get every time in your email or text. I will read every single word of your comments for every class, and I try to accommodate it as much as possible, right? So if you give me some comments, you help me to improve the course for the next summer. Does that make sense? Okay, thank you very much. I see you guys on Monday. Come a couple of minutes early or 2-3 minutes early for the quiz, and have a good weekend. Goodbye.